This is nice to put in your parametric mode, degree mode, make your t-step go from 0 to 360 because you've got to go full circle. That's a nice one to put in there. However, it's a hard one to show work on. And I'm sure you might see something real similar to this tomorrow, and you're going to have to show work. So, two things. Either you give me your calculator, what you put in, give me all the things you put in your calculator, or algebraically, like for instance, you know how remember we subtracted by 4, then we divided by 2, then we did the same for the sign, not divide by anything. This is where you used your cosine squared plus sine squared. So if you plug this in, put it over 1. Okay, this is, and so this will kind of show me that I have a center at 4, -1. This will kind of show me that my x is going over 2, my y is going up 1.
You're going to give us those formulas too, right?
I gave you this sheet. I put this on your desk. This front part is what I'm going to give you on your test only. So this, really, you're developing this from this. You're just applying that to cosine squared plus sine squared. That I didn't give you. I figured you would remember cosine squared plus sine squared equals 1. The ones on the back, I gave you little things to think over tonight. Like these are the, like when we get one of those big functions, everybody forgets to factor and reduce. The vertical asymptote is left in the bottom. The horizontal, you use your rules. We spent a lot of time on that earlier on. And the entrance formula, I thought that I would put on there. But you need to remember, you got to show me work. Remember, I'm not grading this. And here's the thing about, you asked about the multiple choice. I probably put like 3 multiple choice out there. But they're not really multiple choice. You still have to show me all work for them. You get credit based on your work only. However, I put them there to kind of guide you to what I want you to look for, how I want you to answer it. And I'll show you that in a second. There's a good example on this, one of these pages. Let me just check. Okay, it's not on this page. It might be on the other page. It's not on this page. All right, but say I gave you this. This is on one of your other ones. I think it's on the next one, or it was on number 2. It was on 2, when we did this on 2. For instance, this is a radical underneath the denominator. If I just kind of felt that everybody looks at it quick and says, oh, that's 25 times 25, so you can't use 25, you can't use negative 25. But it's really an interval. Because when you map out your negative 25 and your positive 25, this is a parabola that goes like this. So you can only use this little piece in here. So I gave you the intervals as multiple choice. Because I want you to realize it's an interval. It's not just 2 numbers to answer to me. But you still have to show all your work. I left the multiple choice there. Ms. Fernandez and I agreed to kind of take them out, but I kind of left a couple of them in. And I thought that that might be more your advantage over an honors. So that was my decision. You know, an honors doesn't get a multiple choice at all. But I thought if I left it there and you can kind of say, oh, this is not just 25 and negative 25, but it's an interval with 25 and negative 25. So how did I get this? So then maybe that'll lead you to remember. So I've tried in a couple of them to do that. All right, this one, this is a nice one. Using your formula, your interest formula. Remember your compounding? Your compounding annually is 1, monthly 12, quarterly 4, daily 365. Continuously, you have to use per. And that one's a unique one. Remember, even though I gave you a decimal in your percent, you got to flip it to a decimal. That's still a percent. Move it 2 places to the left. Money rounds to 2 positions.
What's per?
Per is anything that says continuously. Your principal times your base E raised to your interest rate times the time. It doesn't have any compounding in there. It's a continuous one, so it's a special formula for PERT. So whenever you see the word continuously, you're going to use PERT.
It's P equals.
No, A equals PERT. I'm actually having that on your formula sheet, Will. Look on the bottom of your first page. I put it there. Stop me if you have any questions. Okay, these were a lot of the ones with the rates and the principals and investment, decrease, increase. We want to know how much will be in the account after 20 years. And it said state to the nearest dollar. Again, fill in your pieces. Be careful when you do it in your calculator. You're pretty much probably used to yellow ones. Once you raise to a power, you can put the times up there, but you can't do it on the black ones. Okay, here's one. Your bacteria is growing continuously. So we're going to use PERT in this. If the specimen contains 6,000 units of bacteria and grows at a rate of 10.2% per hour, how long will it take to make 32,300 units of bacteria? So you're going to put it in your PERT. And normally bacteria grows exponentially. You know, it's something that you open your bread and it's got a little green. And 2 days later, it's got a lot of green. And you didn't throw it out, so another week goes by and it's disgustingly green. So it grows exponentially. If you want to bring your exponent down, remember take the log of both sides. If you're an E base, you have to take the ln of both sides. ln E cancels out. Anybody have questions?
How many questions are there?
Tomorrow is 10 out of 14. And then I have a 7. I have a 7 on part 2 problems for the next day. I think it's 10 out of 14. So if you decide you don't like a problem, you don't like a log problem, omit it. You know? But I would try them, omit what you know, after you're done at the end, go back and omit things you couldn't fill in. This is a nice one, your parametrics, and I did give you the formula on the bottom of the page to help you set it up. The pitch to him is 3 feet high off the ground by the time he makes the connection with his bat. So that's what gives you a vertical shift of 3 up here. Again, it's a parabolic path. This is your horizontal distance. This is your vertical distance. Horizontal versus vertical. And your parameter is time. That's what's going along here. Remember to watch your T-step on this. Because if you set your parameter for an ellipse, you went from 0 to 360. If you're hitting a ball, maximum 10 seconds, 8 seconds, 6 seconds. So you're going to go from 0 to maybe 8. And a 0.5 T-step. Don't go too small. So this guy, and I need 3 decimals on your answers. Remember 3 decimal places. Okay, if you have trouble, here's the thing too. If you can narrow it down, once you get between here and here, and I wrote both of these out because I don't know where you're at with yours, but once you get between here and here, and you need to get a little closer to where this is, set this so that your table starts at one of them and goes to 0.001. You can always jump ahead. You can even do 0.01 until you get a little closer. You want to know when you're 373 feet away. So obviously you're closer to the 4. I think that says 371. I wrote most of them over. I didn't write this one over for some reason. So you're closer to this. As soon as you hit 4, you're going to notice it real close. And it's real close to this. As close as you can get to 373. This is the guide to watch. Did you clear 10 feet? That's your vertical distance. So, yep, I did clear 10 feet. And my ball is 36 feet over that fence. So I cleared the fence. So do we make a home run? We make a home run. Okay? So that's what I'm looking for. Remember to go 3 decimal places, as close as you can. If you can't get any closer, at least write down the part of the table that you're looking at. Or at least write down the 2 pieces that it's in between. Because I'm not grading these. So they're looking for 3 decimal places and pretty exact. So give them enough information so that they know you know what you're doing. Okay, here's bacteria growth. It's an exponential growth. This is your initial. This is your rate. Your time in hours is every 5. This is x divided by 5. So we're going to use this for all of these questions. You're just putting in the hours. That's your x. Now shortcut through this, which is nice, is put this in your y equal in your calculator. Even if your graph doesn't come out where you can see it, if you don't want to change your window, you can still find it, the answers in your table. So then go to where it says 2, pull out that y. Go to where it says 10, pull out that y. Jump down to 24, to 168, pull out that y. This y will probably, I don't know how this will read, it'll probably say 0. If you scroll over it, it may or may not give you that. No, not 0, I don't know. Actually, I don't even know what it will say. It might have the D on it in your table. It probably will. Because it's a lot. It's moved 18 decimals to the right. So I'm pretty sure it'll probably say with the E. And I don't care which way you do it graphically, as long as it doesn't say algebraically. You can go either way with your graph or algebraic. As long as it doesn't say specifically. Okay. Here's a population of a town decreases. They wanted to know the rate. Now the rate is very small. Remember, a rate is like a little decimal. So start out with your formula. You have an exponent there. We just don't have what's inside of it. Don't raise this to the 10th power. Only this gets raised to the 10th power. This is a factor. So if you divide by this, then, like if this had a square, you would take the square root of both sides. Since it's raised to the 10th power, you can take the 10th root of both sides. And then solve for r. It's got to be a really small number because it's a rate. Remember when we graphed these and we did an intersect with this? We graphed the first one. You can graph both of these. You can put in your y1, 75,000. You can put in your y2, 88,000. 1 minus x raised to the 10th power. You can graph these. Even though you can't see it, because it's so small, it's going to be sitting right along your axis, it's still there. If you do an intersect, it's still going to find it. And maybe set your x window so that you can go from 0, 0 to 0.0, 0.5 or 0.5 even. And I'm okay if you solve that graphically. This one. This is a nice one because this also ties your limits in here. It's a transformation graph. You're going to start with your core graph, which is any exponential 2 to the x. 2 to the x has a domain of, it can use any x value that it wants to. It just can't come to the x-axis at all. It can't use a y of 0 or any negatives. So we start out with your basic domain. and we start out with your basic range. This is to your parent graph. Now, remember, go to your x first. Your x says shift, and I need to know the right words. Horizontal shift, 1 unit to the right. Then come out here, there's your negative, there's your reflection near the y in your x-axis. Then the last thing you do is a vertical shift up 3. It's the vertical shift that's going to change. The reflection is going to change your range in your domain. This was your asymptote here. If after you do this, easiest way, once you come down like this, and you shifted it down, your asymptote stays the same, but your range changed. Your range went from negative infinity to 0. It flipped it over. Now, when your range moves up 3, we can add 3 to this. We can add 3 to this. So your new asymptote, your new range. I usually like to do mine like that. Start with my original and apply that transformation to your domain and your asymptote. This is a nice limit problem, because as x approaches infinity, here's my x value. I'm looking at this gray line. As x keeps going here, am I approaching one y value? Is my gray line approaching one y value? No, it's going on and on and on. So I have no limit. Okay? As x approaches negative infinity, am I approaching one y value? And what's that asymptote at? What's that y line that's not letting that go any higher than that? 3. Y is equal to 3, right? So eventually I'm approaching the y equals 3, but never touching it as I go to negative infinity. This is a good way to like tie in your limits with this. I'm hoping you get a little bit more comfortable seeing the word limit, seeing what they're doing. It's just looking at your horizontal asymptote, the same thing that we did before. We're just renaming it a little bit differently. And my goal is so like if you go on to calculus at any point, when they start talking limits, you'll say, oh, I know that. We graphed those. We saw where those end behaviors went. Any questions on this one at all? I gave you kind of a variety here. Most of the things that had interest problems and things like that. And then this last one, oh, this is the solution. Okay. We did this way back, probably September, October. Okay. I want a solution set, and this is one of the times I will probably give you a choice here, a multiple choice. Just because I want to guide you to what you're looking for. If you look at that problem and you don't know what it looks like, you don't know what to do. So I kind of say, oh, you got intervals going on. Oh, you must have factored, because these kind of look similar through here. They're similar, so I must have seen factors of those somewhere. So when you do this, just like you set your quadratic equal to 0, you set your inequality equal to 0 the same way. So move this over, and you're going to end up with this. Now, normally if it's an equality, you find me your 2 points, which is you would find me these 2 points. Can you even see what they must be? Pretty close. That kind of helps you get your factors. So you're going to factor this. You can factor this any way you like. You can do a times c. This will give you negative 24. What are factors of negative 24 that add up to 5? Good. 8 and negative 3. Pop an x next to them. So I have 2x squared plus 8x minus 3x minus 12. These are your critical values. What can I take out of this first grouping? I'm left with x plus 4. I need this grouping to come up with an x plus 4. What can I factor out? Negative 3. X plus 4. So here's my common factor, and here's my factor that's left. set them equal to 0. Those are your critical values. Now, you can plug this into your calculator. If I want it greater than or equal to 0, do I want y values that are negative or positive? What kind of numbers are greater than or equal to 0? Positive numbers. So all I want to do is look at my table. To the left of -4, are those y values positive or negative? Positive. Between here, negative. 2 and greater, positive. Or say, well, this is a quadratic. It's got a positive a, so it's opening up. Just kind of trace your quadratic in here. Shortcut. Anything above the line, positive. Anything below the line, negative. And I want the positives. So I want this piece and this piece. This is one of those where I gave you the choices to kind of help you out. But you still got to show me all this work. Okay? Remember doing these? I will be back in September. Basic functions. I did the domain for each one, but then I combined it over here. When we combine the two functions, you always go to the left. You put this, go to the left. So whatever f at x is, plug it into the x at g at x. And then just resolve and do your domain restrictions. I gave you on the back of this your 3 domain restrictions. I'm not giving you the back of this on the final part. And give you the front part. So here's your domain. Three, I wanted to hit one of these. These are one of your rational functions. And simple way to do this. You had to get this into one term. If there was more than one term and we had to subtract it, we had to find, we did this a while back, we had to find a common denominator. I didn't go that difficult, I left it simple like this one. You already are one term, so you have 2 things to do. Can't factor and reduce anything here. It's irrational. You take your zeros of your numerator, your zeros of the denominator, you put them on a number line. So take whatever's in the numerator, set it equal to 0, solve for x. Take what's in the denominator, set it equal to 0, solve for x. Put it on a number line. Now, because this has an equal sign, the numerator can follow that one. So for the numerator, it can be filled in. For the denominator, it can never be filled in because your denominator cannot equal 0. A 1/3 would give me equal to 0 down here. This one has to be open. And now where's my positives and negatives? You have to put that in your calculator. Look at a little graph. I could see to the left of -1/3, y am negative. I could see in between. And then just pick the one that works for you here. And this probably drops back down. I just didn't drop it back down. Yeah, because this would be a -1/3, so this drops back down here. So it stays positive for a short time and then it drops back to negative. Look at your table, look at your graph. You wanted the positives. So you wanted this in here. And write it as an integral. Very close problem. And you do get a choice. You get to omit 4 of them on your first part. This one, a little bit messier. Determine domain and range and sketch it. Your denominator, underneath a radical can never be negative, obviously. So that in itself we have to worry about. But then when we take apart your fraction, that denominator doesn't have any restrictions. There's nothing I can put into x to give me a 0 or to give me a negative number. Right? Because I'm squaring. Anything I square gives me a positive. So there's nothing I can put in there that my answer won't be greater than or equal to 1. So I don't even really have to consider it. I really just have to consider the numerator. And so I consider my numerator, and that has to be greater than or equal to 0. Factor it, and I find out the pieces that I need. Again, it's going to give you an interval, not just the 2 parts. So graphing it is a little bit weird looking, but you can clearly see in the graph what's happening at the left of the 0, it's positive, right? Of the radical 3 thing, it's positive. It's just that little piece in the middle, there's nothing there. Can't use those. You could leave it as cube root of the cube root of 3, or you could give me 3 decimals. It doesn't matter to me. This one, remember your function notation? This one was pretty good. Solution set, absolute value. The one thing you want to remember is isolate your absolute value. Get the absolute value by itself. In a grade OR, we have ORs that go out on the boat. One to the right, one to the left. So once you're isolated, you take it out, set it up. To the left, you make this a negative, so then you have to switch the sign. Do you see these arrows following these arrows? They have to follow those. They have to go out. Solve each piece. When you divide by a negative, it forces you to flip the sign. This guy's an and statement. Isolate the absolute value. So I'm going to add 2 first. Then, because it's a nice and, I'm going to just drop it down. When I drop it down, I put the same sign here, opposite sign over here. And solve it at the same time. Simultaneously solve it. I would multiply each piece by 3 to get rid of your denominator. Then subtract 1. Here's your solution set. Oops, we're still going here. Here's another one. Another absolute value. Your absolute value is isolated to the positives, to the negatives. To the positives, to the negatives. Alright, solve it. Everybody good with this? This is a nice little problem to put in there. Another function. Everybody good with your functions? Another thing. I don't know that we did this the other day. Piecewise. Just to throw this at you, for some reason. If I have a value, x is 3, what would I do if x is equal to 3? What would I plug into? What would I plug into? The bottom. How come? Good. Because this domain says from 2 on, use me. This domain says anything less than 2, use me. So 3 is coming over here. So all we have to do is plug this 3 into here. And we get y is equal to 7. The compositions made me think of this. Okay. And the last one had a solution set. Again, a rational function. Zeros of the numerator, zeros of the denominator. Graph it and check your table. come up with an interval.